This is video 3 for the light unit. So, let's talk about how the human eye works. Looking at the colors of the rainbow, which I have left up here, we see red, orange, yellow, green, blue, and violet. Indigo doesn't seem to be present, but that's okay. But these are the colors of the rainbow. You may notice that some colors are missing. Where's magenta or cyan? White is also missing. Now it turns out that none of these colors are pure colors, but mixtures of colors. Just like how we can mix paint, we can also mix pure colors. Now many animals do not sense color. They can see only something that is brighter or dimmer. Humans, on the other hand, have 4 kinds of sensors in our eyes for sensing light. First off, we have rods. And the purpose of rods is to sense brightness. Most animals are going to have rods in their eyes. The next thing we have are cones. Now, cones sense color. So we have 3 types of cones. One for seeing red light, green light, and blue light. So those are our 4 sensors. We've got a rod and then 3 cones. Notice then that the red cone, and before I go on here, I've provided a graph which shows the sensitivity of each of those 3 cones. So we have our blue, green, and red. And notice that the maximums that the red cone right here has its maximum sensitivity to green and not red. And that's what happens. What happens is that the eye gets its signals from both the green and red cones. If the signal from the green cone is stronger, we see the color green. To call a signal red, the signal from the red cone needs to be twice as strong as the signal from the green cone. All of these colors then, or all of the colors we see then, are a result of different signal strengths from these 3 cones. So looking at these 3 cones, blue is kind of off to its own, but red and green are really, really close together. So if I kind of take this red cone, kind of draw its maximum sensitivity line down here, we see it's more yellowish to green. So if I want to see something red, that signal has to be very, very strong. Also notice that the red cone can see or can detect some blue light. And looking at the blue cone, its maximum sensitivity is right where we would expect, right in blue. But notice that the blue cone can see some greens also. There's also this overlap right here. So all 3 cones can see or can sense those colors. Just that the signal has to be very, very strong for those cones to be activated. So, if I want to show colors on something like a computer screen or a TV screen, I can try to fool the eye. So, what we're going to do, or what we have done, is we use those 3 dots, red, green, blue, and by changing their strength, we can mix colors to form almost an infinite amount of colors on a computer screen or TV screen. This also leads us to false white. So the easiest way to fool the eye is by using color dots. The screen on your computer is composed of tiny little red, green, and blue dots. Oh, typo there. This should be blue, not red. Using just these dots, these three colors, the screen fools your brain into seeing other colors by triggering the three different colors, or three different cones in your eyes. So what I've done is I've put up the different types of dots that are used. So first off, we have a television. Now this is the CRT, so this is the old-fashioned great big television that has the great big box in the back. So those are the CRT, and notice that the colored dots are more like long rods instead. For PC CRT, now this is a computer screen that's the really big ones. This isn't the flat screen TV screens anymore. Here's an LCD screen, and then another different type of LCD screen. So LCD can go, kind of the rods or the dots. Now let's talk about color blindness. About 5% of all men and about 0.5% of all women do not have both red and green sensors. Or maybe they have less sensitivity in one of those sensors. They are called colorblind, even though they can still see many different colors. Often they cannot distinguish red from green. And that's because with just two sensors, light in the red-green region is not detected by the blue sensor. With only one signal and not a ratio, so the brain can't guess what frequency the light is. So remember that the red and green cones overlap a lot. So, this is just a quick little diagram of the eye. And at the back of the eye, again, here's another diagram from the back of the eye showing where the cones and rods are placed. Now, we do have a test to see if you are colorblind. So, looking at this, if you want to pause it, on the left side, we've got people with regular vision with AC, and then on the right side, what someone with a red-green colorblind, what that person would see. So if you do have a colorblindness, you've probably already seen one of these to diagnose it. Now let's talk about printed color. The printed color works in a similar way to computer screens, but since the inks are usually laid on top of each other, the colors used have to be different. And this is because the colors in the ink absorb light rather than emit it. So they're taking light away from reflected light. So let's say I have a piece of red paper. I would have white light coming in. And remember, white light is a combination of everything. All the different colors get absorbed by the red paper except for the red frequency. That gets reflected. So when I look at, let's say, a green van, the paint on that van is absorbing all of the white light except for green. The same thing with plant life. The reason why all of our plants are green is because, well, green, as it turns out, is not a very good color for energy, for them to go through photosynthesis. So the plants are absorbing all of that light for their photosynthesis except for green. So the colors we use for printing are cyan, magenta, and yellow. Now notice that they are not pure frequencies, but mixtures. So when we talk about mixing light for like a computer screen, we use red, green, and blue. And then by using different strengths and different mixtures, we can get different colors. So this would be something that emits light. So like screens and movie theaters or whatever. When it comes to reflecting light, we use cyan, magenta, and yellow. So when you're in art class and you're talking about the theories of mixing paint, you would use cyan, magenta, and yellow to get the different colors. When you are in a movie studio talking about getting different lights, you'd use red, green, and blue. Also, if you are into stage production, like if you're putting on a play, we use red, green, blue stage lights. And then when you turn all of them on, you get white light on the stage. And then by adjusting the strength of each of those colors, you can get different kinds of mood lighting on the stage. All right, now that we talked about colors, let's talk about images. So the eye manages to give us amazing detail about objects. Think about the smallest thing that you can see. So even ones that are far away, we can see with pretty good accuracy what something is far away, giving some very good detail about it. So this is enabled by the fact that we can create an image of an object in our eye. Now this concept of image is also critical for understanding how holograms, mirrors, cameras, microscopes, and telescopes work. So let's begin with a camera. And we're going to start with something called a pinhole camera. This is the simplest kind of camera. What it is basically a flat sheet with one tiny little opening in it. And the opening's so small that we use a pin to make that hole. So we take a pin and we poke it through a piece of cardboard or something. So that's why it's called a pinhole camera. So it makes use of the fact that light travels in a straight line. So we've talked about light before, how light has both properties of a particle and a wave. So here we're taking advantage of the particle nature of light. Light kind of behaves like a particle in the fact that it travels in a straight line, more or less. It does that only because its wavelength is very, very, very short. So that packet of light behaves kind of like a way a particle would. So light comes in little packets of waves, which we call photons. So this stream of photons kind of acts like a particle and allows light to travel in a straight line. So a pinhole camera consists of a box with a small hole on one side and film on the back. Light from the object passes through the hole and lands on the back. So here's a picture of this. Now here I have a person standing, got their arm raised. Light from the top of their head travels straight, and just a few of those rays are going to pass right through the hole of the pinhole camera and land on this film. Light from the person's foot is going to travel and hit the back of the film. Light from the person's middle is just going to travel straight through. And you can imagine there are an infinite number of rays of light that person's emitting going off of them, so we can get a complete image. Now, one thing I do want you to notice is that the image is always upside down. So on the back of your eye, all images are inverted. They're all upside down. Because if you think about it, your eye acts like a pinhole camera, where the pinhole is the pupil of your eye. So if I want to construct a camera using this, and we can, if the hole is too large, the image will be blurry because it's allowing too much light in. So there's too many light rays coming in. We're not going to get a very detailed picture. If the pinhole's too small, the image is going to be dim and hard to see. So with the human eye, we have muscles around the pupil which help to enlarge and constrict the pupil. So if you're in very low light situations like at night, your pupil will enlarge to allow more light in so you can get a clear image. And when you're in bright daylight, the pupil will contract and restrict a lot of that light so that you can't, so it doesn't allow in too much light, and just keeping the image from being blurry. So again, your eye acts like a pinhole camera. The pupil is the pinhole. The retina, which is the back of your eye, the rods and cones act like the film. Each sensor then sends a signal to the brain, which then interprets the image. Since we have a pinhole kind of example, all images on the back of your eye, or projected in the back of your eye, are upside down. This is what's kind of fun, is that you can wear special glasses that will flip things upside down. And if you wear those glasses, everything looks upside down. But if you keep them on for about 2 weeks, that will become your new normal. You will be able to pick up things and operate perfectly fine, like you never had the glasses on at all. When you take the glasses off, everything then appears to be upside down for about another 2 weeks until your brain can readjust. So your brain is very, very adept at changing its version of normal. So, something that's key to recognize then is that the eye is a device for measuring the brightness and color for different light. In the next video, we will talk about mirrors.